Hey class, it's Bob again, and in this video we're going to talk about something called an economic production lot size. We talked about EOQ, and this is somewhat like EOQ. Recall EOQ was the economic order quantity, and the EOQ's job was to minimize the sum of my ordering costs and my holding costs. Okay? So with EOQ we're ordering something. We just get it all at once. And you may recall with EOQ our inventory looked like this. Over time, the quantity of inventory would arrive and we'd use it up. We'd get replenished, called instantaneous replenishment. The order all comes at once. So our inventory jumps back up. And then we use it up over time. Our inventory level goes down over time. We get another order, instantaneous replenishment, and we'd use it up over time. And that was the EOQ model. Okay, economic order quantity. Now, there are other situations where we have non-instantaneous replenishment, where perhaps we produce our own inventory. So maybe I produce my own carburetors, and does anybody use carburetors anymore? Let's say I produce my own transmissions for my own automobiles. And what happens is I can produce those at a rate of, let's say, 50 a day, and I use them, I put them in automobiles at a rate of, let's say, 40 a day. Okay? So what would happen is I would produce them at a rate of 50, okay, and use them at a rate of 40 per day. So at the end of day one, I would have accumulated 10 transmissions because I produced 50 and I only used 40 of them. So I've accumulated 50. At the end of day two, I would have accumulated 20. So I'm accumulating transmissions at a rate of 10 per day. So if you look at just P minus D, that tells me how many I produce minus how many I need, daily demand for a product, and that's the amount I accumulate each day. Okay, so in this problem, I've got to figure out, just like EOQ balances the amount of my ordering costs and my holding costs, this balances, instead of ordering costs, something called setup costs. Okay, we're going to use that same symbol, CO, that we use for ordering costs, but now that's going to represent setup costs. So every time I set up to produce something, I experience setup costs, because what would happen is I would keep accumulating transmissions. At the end of day 3, I'm going to have 30. Okay, at the end of day 30, I will have accumulated 300 of these. Okay, do you see that at the end of day 30, I would have accumulated 10 times 30, 300, and now I can just coast. I can stop that production run of transmissions, and I've got 300, and I could go for 7.5 days before I would need to start producing again. So my demand could, or my accumulated inventory could just come back to 0. I would start producing again, and it would start accumulating again. Okay? So I've got to decide on a particular production run size. Do I go and produce a production of 30 times 50 or 1,500 units, and over that time period accumulate 30 times 10 or 300 units? Or should I make a longer production run where I produce for, let's say, 100 days, and over that 100 days I would produce 5,000 transmissions and accumulate 1,000 transmissions. So I've got to decide what's the appropriate production run size, and that's Q. We're going to use the Q to represent now a production run size. So that's the kind of decision I make. And I face the same kind of challenge I did with EOQ. The larger the production run, in other words, the longer I sit there and accumulate, and therefore the larger my average inventory becomes, and the larger my holding cost becomes. However, the larger the production run, the fewer times I have to set up the equipment, the lower my setup costs. Okay, so it's like the EOQ model in that we have setup costs, which are analogous to ordering costs, and we have holding costs once again. You may recall that in the EOQ model, my holding cost was based on my average inventory. Well, in this model, your holding costs will also be based on your average inventory. However, in EOQ, the average inventory was just Q over 2 because you had instantaneous replenishment. In this model, my average inventory equals half of my maximum inventory. So let's say I'm accumulating, and then I'm using. I'm accumulating, and then I'm using. And here's the start of a production run. Here's the start of another production run. And I'm producing during this time period here, and I'm producing during this time period here, and this little time period in here, or here, I'm only using that which I've accumulated, okay? Well, this maximum inventory is important because we'll call this IMAX, or maximum inventory, and my average inventory will equal half of my maximum inventory. So here's average inventory. Okay, average inventory equals IMAX, not the theater, the maximum inventory over 2. Okay, for reasons similar to why average inventory equals half of the quantity you order in the EOQ model. So here's the first thing to remember. My average inventory equals half of my maximum inventory. Now, what does IMAX equal? What does your maximum inventory equal? Well, that's going to equal the number of days in your production run times the amount you accumulate each day. So let's say I decide on a production run size of Q. So let's say I decide to produce a 1,000, a batch, if you will. A production run is another word for a batch. A batch of 1,000 units. And I produce those at a rate of 50 per day. Doesn't that mean that I would be producing for 20 days? So in this example that I just made up, I said that Q equals 1,000 and P equals 50. So what I'm saying is I'm going to do a batch of 1,000 transmissions, and I can produce them at a rate of 50 per day. So that means Q over P is 20. 1,000 over 50 is 20. That means I'm going to be producing for 20 days in a row, after which I'm going to stop producing and just use up that which has accumulated. So Q over P is the number of days in a production run. And if I look at that times P minus D, which recall P minus D is the amount I accumulate each day, now I've got the number of days in the production run times the amount I accumulate each day. And that's where my inventory peaks. Okay? So Q over P is this distance from here to here. It's this, if you can see back on my little chart here, okay, it's this distance right here from the beginning to the end where I'm only producing. Now, each day I'm accumulating P minus D, so that gets me my IMAX. The number of days in the production run times the amount I accumulate each of those days. Okay? Of course, if you take IMAX divided by 2, that gives me my average inventory. Okay? If you take IMAX over 2 and multiply it times CH, then I get my annual holding costs. My annual holding costs. Okay? If I take my annual demand and divide it by that quantity I'm going to produce, then that gives me the number of production runs I'm going to have to take. D over Q is the number of production runs. Okay? If I multiply that times the cost of setup, that's my total setup cost. Because every time I shut things down, I've got to start things up again. Maybe that involves creating or cleaning equipment or setting up equipment to do a particular thing. And that has some cost. There's probably some labor involved, perhaps some parts, etc. So setup cost, the CO. If you add these two together, I've got my holding cost plus my, let's see, D over Q times setup cost. This is my total cost. Okay. And EOQ, I'm going back again. EOQ, recall, minimizes the sum of my holding and ordering costs. Well, what I want to do now is minimize the sum of my holding cost and setup cost in this scenario. And the formula that does that is right here, and that's this Q star. Square root of 2 times annual demand times my setup cost over, open parentheses, 1 minus D over P times my holding cost. So this formula right here, which you don't need to memorize, it would be given to you, will spit out the optimal production quantity size that will minimize the sum of my holding costs and my setup costs. I'm going to pause it. We'll come back with a quick example. Okay, so here's a quick example. In this situation, we're trying to figure out what's the optimal batch size, the optimal production lot size. And we define optimal as minimizing the sum of my setup costs and my holding costs. So setup costs and holding costs. Now in this situation, every time I set up to run a batch, to run a production lot, it cost me $200. In this example, my annual holding cost per unit is $10. And in this example, I have the capacity to produce at a rate of 150 units per day, and I need or use 50 units per day. So that's where all these come from. Now, if I plug that into my formula, I get Q star equals the square root of 2 times, I didn't include annual demand. Let's say annual demand is 1,000. Okay, meaning I need, well, no, that's not right. Annual demand would be a function of daily demand. Let's say I operate 250 days per year. So annual demand would equal 250 times 50. So annual demand would equal 12500, 12,500. Okay. Now, let's finish this problem out. So I've got 2 times 12,500 over, or times 200 over 1 minus, with the ratio here is 50 over 150. So that's 1 minus 1/3. That's going to be 2/3 times 10. Okay. Now, if I plug all that in to my calculator, okay, you get about 866, which means that I'm going to produce in batch sizes of 866. So that means that my inventory will accumulate for 866 divided by 150. That's the number of days my inventory will accumulate. That's what, about, close to between 5 and 6 days. It's going to accumulate at a rate of 100 per day. So my maximum inventory is going to peak around 866 over 150 times 150 minus 50. Okay. So close to 6 days accumulating at a rate of 100 a day. My maximum inventory is going to be around 100. My average inventory is going to be, my maximum inventory is going to be around 600. My average inventory is going to be around half that. Okay. So practice computing total cost, and I've got to shut the video off at this point.